Hierarchical structure of IP addresses. In this video, we're going to look at why IP addresses have a hierarchical structure, the importance of this, and the benefits that we gain by IP addresses having a hierarchical structure. So what do we mean by hierarchical? So before we talk about why IP has hierarchical addressing structure, we need to know that there are two types of addresses, flat and hierarchical. A flat address has no partitioning in it, and the range of numbers are not broken up into a meaningful way. But with a hierarchical address, the address is broken up into ordered chunks which have a meaning. So as an example, with a license plate of a car, that's a flat address. There are no group of numbers or no group of digits in the license plate which have any special meaning. A license plate is just to uniquely identify a car. However, a number or an address like a telephone address, that is a hierarchical address because certain digits in the address has special meaning. So, like I said before, an example of a hierarchical address are telephone addresses. So the first section of a telephone number is the area code, which represents a large geographic area. The next part that follows the area code is known as the prefix, which narrows down that scope to a local area. And the last section, is the customer number and focuses on a specific connection/house. So as an example, this shows the telephone number for the Brent Cross area. So 020, it identifies that this is a London number. The next part, so this is the area code. The next part is the prefix, and this tells us which local area within London it is. So this tells us it's in the Brent Cross area, and then the last four digits would tell us the specific house or the specific shop within that area. So with a hierarchical address, all it is, it's an address where chunks of the address have got a specific meaning. It's different to a flat address. When a flat address, chunks of the address have got no meaning, and the address only has a meaning with the whole address, so with the whole number of digits. So as an example, with the license plate, the whole license plate has a meaning. It means that it is a unique identifier for a car. However, parts of the license plate, so certain numbers of the license plate don't have any meaning. But with a telephone number, parts of the telephone number do have a special meaning in that it helps group things together. So with IP addresses are very similar. An IP address, if you remember from the IP version for a protocol video, an IP address is broken up into two parts, the network part and the host part. And so the network part is the part of the address which has a special meaning in that it uniquely identifies, it is used to group devices together. So devices in the same segment, in the same network, will have the same network part, but will have a unique host part. So with the network part, you used to group all devices together and put them in the same network. The host part is used to uniquely identify the host within that segment, within that subnet. And so if we look at any IP address, the bits of the IP address, so an IP address is 32 bits in length, the bits of the IP address which represent the network part, they will be the same for all devices in that segment. However, the bits that represent the host part, they will be different. So by grouping devices together, this is used to make routing more efficient. So instead of a router having to have multiple routes to reach each host in a particular segment, instead of having individual routes, so a route to reach the device with the IP address 192.168.1.1 and another route to reach the IP address of a device of 192.168.102. Instead of having individual routes, the router can instead have a route which points to the group of devices that have something in common, and using that route, it knows that it's sending traffic to this group and it can reach any host within that group. So we have to look at two important IP addresses for each network or each subnet that have special meaning. So as an example, we're assigned this network to our enterprise 192.168.1.0/24 with a subnet mask of 255.255.255.0. This subnet mask in binary is 24 binary ones followed by 8 binary zeros. The 24 binary ones in a subnet mask identify which bits of the IP address represent our network and which bits represent our host. So this means that any device within this network that lives on this segment, they have to have these first 24 bits in the IP address. So 192.168.1, they have to have that in the IP address, and then this number here, that could be any number. So the two important addresses are the network address, which is 192.168.1.0. This is the first IP address on the network, and the broadcast address is the last IP address, is 192.168.1.255, and the range of usable addresses are between the two numbers. And this is important because we're now using an IP address to identify our whole network instead of using individual IP addresses. So this means that instead of a router having to have a route into each individual IP address, it can have a route to this network, and because it knows that the first IP address of a network or of a subnet has a special meaning, it means it represents that network and all devices in that network. It knows that if it has a route to this network address, it has reachability to all the devices in that subnet, in that segment, because they all are grouped together and they all reside in that same subnet, segment, network. Now, there are 4.3 billion IPv4 addresses. If IP addresses do not have a hierarchical structure, a router would have to have a route for each IP address, meaning each route in the world would have to have 4.3 billion routes. Now, the problem with having such a large routing table is that a routing table is stored in memory. Because it's stored in memory, it means that this a large routing table, the router has to spend more CPU cycles maintaining that table, changing it, so whenever a route is lost, whenever a route is gained, it's always changing it. And it costs CPU cycles in order to maintain that table. It also makes routing slower, because if a router has a very large table, it's going to take him longer to look through that table to eventually find a matching route so that it can forward that packet onto the correct next hop. So our goal as network engineers is to make the routing table on a router as efficient as possible, so that the router can look through that table faster, which makes routing faster. And so by instead of a router having a route to each individual IP address, it can have a route to the network address, and because routers know that the network address has special meaning, it knows that as long as it has this route to this network address, it knows it can reach any device within that network, because this network address represents all of those devices, and the router will still have reachability to everyone there. Now, this image shows how the routing table of a router would look like if IP addresses followed what's called a flat structure. So with a flat structure, a router would have to have a individual route to each IP address. This makes routing very inefficient, because as you can see, this image just shows 3 devices, but imagine if we had 254 devices. That means that R1 would have to have 254 routes to these devices, and those routes would all point towards the same path, which doesn't really make any sense. It's a waste of resources, because surely if these 254 routes, or if these 3 routes in this example are all pointing to the same path, couldn't we just have one route where it says that to reach these group of devices, use this route, use this path, since each device that it needs to reach is going to reside in the same local area? And so with hierarchical structuring, that means we can group devices together based on the network part of the address, and that means that in this case, the router, instead of having 3 routes to reach PC1, PC2, and PC3, it can have one route which says that to reach any device in this network, you can use R2. So as you can see, by having a flat structure, we need to have a route to each individual IP address. This is redundant, because normally the devices that reside in the same network, the path or the route to get to those devices would all be the same. So it would be redundant. It wouldn't make any sense to have multiple routes all pointing towards the same place. So instead, with hierarchical structuring, because we know that certain parts of the address are significant, we know that in this segment over here, all devices in the segment have an IP address, have been grouped together, and their IP addresses begin with 192.168.1. So instead of having a route to each individual IP address, we can have a route to this group and still have full reachability. Now let's talk about the how IP addresses are assigned. So now we're talking about the hierarchical assignment of IP addresses. Okay, so the IANA, they're responsible for assigning global IP addresses, and the IANA are Department of ICANN. So the IANA, they have all the global IP addresses in the world, and they're responsible for the assignment and the management of the IP version for a global address space. Now the IANA don't actually assign addresses or address spaces to companies or to businesses or to ISPs. Instead, they allocate address space to regional internet registries across the world. Some examples are ARIN and APNIC. And these regional internet registries represent large geographical regions. So as an example, there'd be one regional internet registry for Asia, one for America, one for Europe, one for Africa. And their job is to distribute the IP address space within their region. So regional internet registries would assign address space to ISPs. So as an example, if we take APNIC, which is responsible for not APNIC, sorry. If we take ARIN, who was responsible for the American region, its job is to assign IP address space. So it's been given a block of IP addresses that it can assign. Its job is to assign IP addresses to companies, ISPs, national internet registries, and local internet registries within the American region. Now, once address space has been assigned to an ISP, the ISP will use the address space for their own network, but they'll also assign address space to their customers. This is so with an ISP, a regional internet registry, they will assign a large block of addresses to an ISP. Now, the ISP, it uses that block to assign addresses to devices in its own network, but it also assigns global address space to customers, to customers that use the ISP for their internet connection. And so this diagram over here shows the hierarchical structuring of how IP addresses are assigned. The way it works is that the IANA, they've got all the global IP addresses. They would assign blocks to these companies over here, to the regional internet registries, and they wouldn't just assign random address blocks. They would assign address blocks based on a hierarchical structure, which will make routing more efficient. And we will see that in the next slide, how by using a hierarchical structure, it can make routing more efficient even on this scale. Now, the regional internet registries, they normally assign IP address space to ISPs, but they can also assign IP address space to local internet registries and the national internet registries. Now, the ISPs themselves, they're responsible for assigning address space to its customers. Sometimes you get a customer which goes to either a regional internet registry, national internet registry, or local internet registry for its global IP address assignment. But usually, when you ask an ISP to provide internet connections, the ISP will assign you a global address space, so that you're part of their network, and so that whenever you communicate with anybody on the internet, they know that in order to reach you, they have to send this traffic back to this ISP because your internet connection is with this ISP. Now let's talk. Now I'm going to go through an example of IP address assignment. So in this example, the IANA have assigned the 10.0.00/A block to the ARIN regional internet registry, and they've assigned the 172.16.0/16 block to APNIC. Now, when these regional internet registries are assigned a block of IP version 4 global addresses, they're not going to assign those whole blocks to ISPs or whole block to national internet registries. Instead, they what we call assign subnets. So what a subnet is, we know that from the previous video that as shown over here, that depending on what class of IP address you use depends on the subnet mask you use, and determines what part of the address represents your network and which part represents your host. So in this case, if we were assigned a /A Class A IP address or a Class A block, that means the first part of the IP address represents our network, and then the next three parts represent our host. With subnetting, we borrow bits from the host part so that we ignore these rules, and so that we can create custom subnet masks to determine what part of the address represents our subnet or our network, and which part represents a host. So in this case, we've done our subnetting here. So instead of just the first IP address representing our network, we've assigned this address block to AT&T. With AT&T, now the first two IP addresses, the first two digits represent their network, and then the last two digits represent the host. This means that AT&T, any IP address that they assign to any device in the network has to begin with these first two digits. So instead of assigning the whole address block that a regional internet registry has been given, they will assign portions of it, which are known as subnets, which is to improve IP addressing assignment efficiency. Now AT&T, they will do the exact same thing. They would assign from the address block that they've been assigned portions to their customers. So in this case, it's assigned 10.1.1.0.24 to customer 1. Customer 1 will subnet further so that it can then assign subnets and IP addresses to all of its segments, to all of its VLANs, broadcast domains, WAN links, and so on. And with AppNIC, the same thing's happening. So AppNIC's been assigned a Class B block, then it's assigning a portion of the Class B block to this ISP here, City Telecom ISP, who's then assigning a portion of that Class B block, or the portion of the subnet that it's been given to this customer over here. Now, by following a hierarchical structure, it makes routing more efficient even in this example. So as you can see, City Telecom know that AT&T have been assigned this address block. And they know that with this address block, the first two digits have a meaning. The first two digits represent our network. And every customer that joins AT&T for the internet connection, their global IP addresses would begin with 10.1. So instead of City Telecom having a route to all the customers that connect to AT&T. So imagine AT&T is a very large ISP. That's where it's got a Class A block, and it's got 1,000 customers which connect to it. Instead of City Telecom having 1,000 routes for each customer, so one for each customer that connects to AT&T, City Telecom know that no matter how many customers connect to AT&T, no matter what portions or what IP addresses they're being assigned, all the IP addresses will begin with 10.1 because that's the block that AT&T have been assigned. So instead of having a route to the 1,000 customers which connect to AT&T, City Telecom can instead have a route to this network over here, which would get their packet to AT&T, and they would still have full reachability to the customers because in the AT&T ISP's network, the AT&T routers will have specific routes on how to reach devices or how to reach the customer sites. The way it works is that we use a general route to get us to the ISP, and then the ISP will have the more specific routes on how to reach the different customer sites. And so this is only achievable with hierarchical structuring of IP addresses. So because IP addresses have a hierarchical structure and because certain parts have a special meaning, it means that we can group devices together more easily, making routing more efficient because we can replace thousands of routes or even hundreds of routes with a few routes, which makes our routing table smaller, which makes routing more efficient. AT&T would have the exact same thing. Instead of having a route, let's say to customer 2's network, they would have a route to 172.16.1.0.24 because that's the address block that has been assigned to City Telecom. They know that any IP addresses that they assign to customers will begin with 172.16.1, and they have confidence that they can have full reachability to the customer sites that connect off City Telecom ISP. And the ISPs themselves will make use of this grouping in order to make routing inside its network more efficient. So as an example, let's say that customer 1 is a site which resides in New York, and customer 2 and 3, which connect to the ISP as well, they live in New York as well. what an ISP would do, an ISP could assign customer 1 and 2 these subnets, 10.1.2.0/24 and 10.1.3.0/24. And this is significant because these subnets all have something in common. If we were to convert each subnet into binary, you would notice that even though the third digit differs, these subnets or these IP addresses, the first 22 bits are all the same. So as an example, let me convert this one to binary. So we know in binary, this would be so we got 128, 64, 32, 16, 8, 4, 2, 1 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1. So 128, 64, 32, 16, 8, 4, 2, 1. That's this IP address in binary. Let's look at this IP address now. So we've got 1, 2, 3, 4, 1, 0, 1, 0, dot 0, 0, 0, 0, 1, so that's 4. That's 1, 2, 3, 4, 5, 6, 7, 8, dot 1, 2, 3, 4, 7. So that's 128, 64, 32, 16, 8, 4, 2, 1. And now this in binary is going to be 0, 0, 0, 0, 1, 0, 1, 0, dot 0, 0, 0. So 4, 5, 6, 7, 8, dot 1, 2, 3, 4, 5, 6, 7, 8. And so the first 22 bits are A, 16, 17, 18, 19, 20, 21, 22. So if you notice anything about these IP addresses, the first 22 bits are exactly the same. It's these last two bits which differ. And because their first 22 bits are the same, instead of having a root to each individual subnet, we can have what's called a summary root, saying that to reach any network with these first 22 bits, you can use this route. And this can only be done with hierarchical IP addressing. So with hierarchical IP addressing, part of the address have a special meaning. So in this case, the special meaning here is that the first 22 bits are exactly the same. So instead of having a route to each individual network, we can have a summary route which encompasses all of those networks because they have similar bits, because their first 20 bits are the same, making routing more efficient because we can replace 3 routes with a single route. So we reached the end of this video and we've seen how the hierarchical structure of IP addressing can help with routing, and it makes routing more efficient. And we've seen that by hierarchical structure, all it is that certain parts of the IP address has special meaning. And by grouping devices together based on that meaning, it makes routing more efficient, because instead of having to have loads of specific routes, we can have more general routes, we can have more general routes and still have full reachability across the internet. I hope this has been informative for you, and I'd like to thank you for viewing.